Okay, so we have just determined that the given series converges on this set, a half-open interval between 2 and 4. Recall that a power series defines a function. So this conclusion means that because the power series is convergent only in this range, it means that the function defined by this power series has this interval as its domain. So this here is the domain of the function given by the power series. Okay, let us proceed on to example number 4, in which we will try to answer the same question for which values of x is the given series. In this case, it is k factorial times x to the k summed up from k equals 0 to infinity. So for which x's is this series convergent? The first thing to do is, for this series, as for most other power series, first apply the ratio test. So that's what we will do. Apply the ratio test. Okay, according to the ratio test, we must look at the limit. K goes to infinity, ak plus 1 over ak. Now, in this power series, ak is the entire term over here. So this is the ak. So now the limit we have to compute is the following. It's the absolute value. For the numerator, I have ak plus 1. Notice what I did was I replaced every k in the kth term with k plus 1, and it is divided by the k factorial times x to the k, so the ak term. All right. First of all, I'm going to try to cancel as much as possible. So it is clear that the powers of x will cancel out. So what remains is the limit as k goes to infinity, k plus 1 factorial times x divided by k factorial. Now, observe that the only factor in this expression that can become negative is x itself, right? Neither k plus 1 nor k factorial can be negative. So I don't need to apply absolute value to these two positive numbers. I can just as well write this simply as absolute value of x times k plus 1 factorial over k factorial, right? This is the only factor that can be negative. Everything else is a positive expression, so these two limits are equal. Okay, now of course I'm looking forward to canceling out everything in this ratio. So recall that k plus 1 factorial is the product of all the positive integers starting from 1 up to k plus 1. So let's write in k. We have k and then times k plus 1. And in denominator, I have k factorial. So that would be the product of all the positive integers starting from 1 and going all the way up to k. So we'll have, we have 1 times 2 times 3 and so on again, up to k. Great. So as you can see, these factors appear both in the numerator and in the denominator. And so therefore they will cancel. All I'm left with is limit, oops, let's put the equality here, is the limit as k goes to infinity, absolute value x times k plus 1. Now, in order to compute this limit, observe that x does not depend on k. So this is a situation similar to what we had in the previous example. X is independent of k, therefore in the limit, this part is effectively a constant. So I can write it as absolute value x times limit k goes to infinity of k plus 1. All right, but this is a very simple limit, right? So it's trivial to see that the value of this limit is plus infinity, and so we will have absolute value of x multiplied by plus infinity. So the only possibility for this number not to be infinite is for absolute value of x to be 0. So this is equal to plus infinity if absolute value x not equal 0. Okay, and since we were applying the ratio test, it follows that for all the x's that are not 0, value of this limit is plus infinity. And so, of course, the key property of plus infinity here is that it is bigger than 1, right? And that's the only thing that matters for the ratio test. And so the value of this limit is bigger than 1 if absolute value x is not 0. And therefore, our conclusion is that this series is divergent for x not equal to 0. Right? What happens for x equal to 0? Well, let us look here. When x is 0, all the terms of this series, except for the very first one, vanish. So I should say here, I want to emphasize that 0 factorial, right? So that is something that happens when you plug in k equals 0. We will agree to say that that is equal to 1. So when x equals to when x is equal to 0, all the terms but the very first one vanish, and the very first one is, well, it's a finite number, it's 1. So the series is convergent for x equal to 0 only. Right? So if we were to visualize the domain of this function, right? This power series defines a certain function. So its domain would consist of a single point. So this would be the domain of this function k factorial times x to the k summed up from k equals 0 to infinity. It's a very, very useless function. It can only be evaluated at one point, and at that point it gives you back 1, in fact, as we just discussed. So we have seen an example of a series which converges on a nice reputable interval. This is the sort of degenerate case where your interval is so small it's effectively a single point. Now, let us consider one last example for this topic. example 5, to show that occasionally not only you can have one endpoint case in the sense that this interval of convergence gets really short, right? So this interval of convergence gets really short, so short that it becomes a point. You can also have the other endpoint case where the interval is so large it becomes the entire number line. So let us find the domain of the J0 Bessel function given by the following series. J0 of x is equal to the sum k from 0 to infinity minus 1 to the k x to the power 2k divided by 2 to the power 2k times k factorial squared. So this function has something to do with mathematical physics. So it is somehow relevant when you try to compute the shape of a vibrating drum. So if you take a drum, tap on it, the membrane vibrates, and in the radial direction its shape is described by J0. Well, not necessarily by J0, but by the functions of this type. Right? And since this function is given by series, finding its domain just means that we want to determine x's for which this series will converge. So that is, we have to find x's for which the series of J0 converges. And that is something we know how to do. Okay, specifically we will go ahead and apply the ratio test. So, to do that, let us write down again the limit we're about to compute. Okay, all right. Now, what is ak plus 1? In this case, we have a tricky expression for ak plus 1 because a lot of terms in here depend on k, so let us be a little bit careful. So what do we have? So let us draw a big fraction and put everything ak plus 1 related on the top and all the terms ak related on the bottom. So on the top we will have minus 1 to the k plus 1 times x to the power 2k plus 1, right? So we replace this k with k plus 1, divided by 2 to the power 2k plus 1 times k plus 1 factorial squared. And on the bottom, we will put minus 1 to the k. We'll just rewrite this expression. Minus 1 to the k, x to the 2k divided by 2 to the 2k times k factorial squared. Okay, and then we have big pair of absolute values on top of everything. Okay. So now let us try to simplify this expression, let's see, we are looking at the limit as k goes to infinity. Then inside of this ratio, we can just drop the -1 to whatever power altogether, because its absolute value is 1, so we can disregard it. It has no impact onto the magnitude of this entire expression. So let us discard those two factors, and we're looking at the ratio of. So on the top, we have x to the power 2k plus 2. That's what I get if I multiply this product into exponent, divided by 2 to the power 2k plus 2 as well, multiplied with k plus 1 factorial squared. Okay. And this entire thing is divided by x to the 2k divided by 2 to the 2k times k factorial squared. All right. We will have to cancel these two powers of x. The same goes for the powers of 2. And then we'll leave factorials to deal with them later. All right. So far, our limit looks like so. We have x squared divided by 4. So this 4 comes from the 2 squared. And then multiplied with k factorial times k plus 1. Everything squared. Right? So this expression here comes from k plus 1 factorial. So k plus 1 factorial is precisely k factorial times k plus 1. So that's what we put in here. Now it is multiplied by k factorial squared over 1. Right? So everything else in the second quotient has cancelled already. Great. So now we can take care of the factorials. We'll have the limit k goes to infinity, x squared over 4, and then in the numerator, let us put k factorial squared, and in the denominator, we'll place this expression squared. So it will be k factorial squared multiplied by k plus 1 squared, right? So here we have product of two factors, k factorial and k plus 1, and it is squared. So we square both factors in this product. So this is effectively the use of the rule. We have product of a and b for some numbers a and b, and it's squared. So what we do is we replace it with a squared, b squared. Okay. So of course the whole point of doing so is that we can now cancel this k factorial squared with this one, and hooray, we arrive at something very nice and manageable. We will look at the limit, k goes to infinity, absolute value k x squared over 4 times k plus 1 squared. Okay, so now our goal is to compute this limit, and then will be the answer. This will be the limit resulting from the ratio test. Of course, to do this, you can go ahead and compute it right away. It's an easy limit to compute, or we can play a little bit with it to make the answer more apparent. So first of all, observe that the only factor that can change sign at all is x, and that is squared. So everything in this expression is positive. So there is no need to absolute value altogether. right? Everything is positive. X squared is positive. These two factors are positive. So I can just write it this way. Secondly, the only thing that depends on k is this factor in denominator. I can take the rest out of the limit. So that leaves me with the limit k goes to infinity. Oops, I should have left some space. Let me put it here. I can take x squared over 4 outside the limit. And then in the limit, I have just 1 over k. Oops, that should have been not factorial but squared. K plus 1 squared. And now, ta-da! This entire limit is, of course, 0, right? You have 1 over k plus 1 squared, k goes to infinity. And so, all in all, you have x squared over 4 multiplied by 0. So that is going to be 0, regardless of the value of x. So let us think about what this is saying. We applied the ratio test to our power series, and the output of the ratio test is 0, which incidentally is less than 1. So by the ratio test, it means that this series is absolutely convergent, no matter what is the value of x. Right? Because this limit is 0 regardless of what is the value of x. And so, in terms of the domain of J0, this is saying that its domain is the entire number line. And so this completes this final example. And so we see that unlike in the previous two cases, our domain here is just the entire number line. So if we were to visualize it, we would get everything that we can see on the number line. So that's the domain of J0.